Okay, everybody. So now we've had a look at meteorites and we've come to the conclusion that the Earth is about 4.56 billion years old. Now let's have a think about what was going on in some of the individual portions of the geologic timescale. So now the Hadean itself, there's not much really to say about the Hadean. So the Hadean, obviously, for a lot of it, the Earth was just a big sphere of magma. So during the Hadean, we did have the formation of the Earth's core, so iron-nickel alloy, so essentially iron and nickel alloyed together, began to form in that magma ocean, and big droplets of it would sink to the centre of the Earth where they formed the Earth's core. So that was happening during the Hadean. During the Hadean, we also had the formation of a very thin, crispy crust on the surface of the Earth. So we did have some rocks in the Hadean, but that crust that formed would have been highly unstable. You have to remember, in the Hadean, the magma ocean would have been constantly churning underneath, so that very thin, very early crust would constantly be destroyed. It'd be sucked down into the mantle, or the mantle would push up and just destroy it that way. It would not have been very stable, and it wouldn't have lasted very long. So any crust that formed in the Hadean would have been completely destroyed. Okay, so let's move on to the Archean, because things are actually happening in the Archean. Well, in the Archean, we see the appearance of the first stable crust. That's the first thing. So we actually have pieces of crust that are not, being destroyed by mantle convection or mantle processes. So this crust is going to hang around now. Now, these continents that form are going to be very small. They're going to be a fraction of the size of the modern continents. What else are we going to see? Well, we do have the formation of continental crust in the Archean, but we also have the formation of oceanic crust. So now we have our two different types of crust. We have the continents and we have the oceans. And I'm sure, as you know, from very, very early in the course, because the continental crust is naturally so thick, it will naturally sit higher than the oceanic crust. So, of course, that forms these very, very large depressions, which we refer to as ocean basins. So what's going to happen with these very, very large depressions? Well, we have an atmosphere. That atmosphere contains water. It's going to rain. And so during the Archean, we start to see the formation of oceans and lakes. And we can see this, in the rock record. We can begin to see we have minerals which we know have been in contact with water from a sea or lake. And so we know there were definitely surface bodies of water around. So the atmosphere itself, which contained this water vapour, would have been very, very carbon dioxide rich. So it would have been a nitrogen carbon dioxide atmosphere. So obviously that means practically no oxygen. And any oxygen that was produced was instantly used up in chemical reactions. So, if you took a time machine back to the Archean and you stepped out of your time machine onto the surface of the Earth, you would start suffocating instantly. So another thing that happens in the Archean, which is very interesting, is we begin to see the appearance of life. Now, this life is obviously going to primarily be found single-celled organisms, and we believe it was mostly limited to the oceans and the lakes, the bodies of water. So we see life beginning to, or the first indications of life, should I say, around 3.5 billion years ago. There is some evidence to suggest that maybe life existed before 3.5 billion years ago, but that evidence is a little tenuous, so we can't be 100% certain whether it's correct or not. In terms of the Archean rocks that we have, the vast majority of them have been very heavily metamorphosed. That means we do not have the original rock, so we don't really know what's happening. We can tell what was continental crust and what was oceanic crust, but apart from that, things get a little bit more complicated. Now, in the Proterozoic, what we begin to see these small continents begin crashing into each other to produce much larger continents. Now, you have to remember, the mantle in the Proterozoic is still very, very hot. That means it's convecting much, much faster than today. And that means plate tectonics is occurring at a much faster rate. So these continents are banging into each other at from a geologic point of view quite quickly. So what happens is we begin to form these larger continents. And these larger continents are important because they form what we refer to as cratons. And the cratons are the cores of the continents. They make up the stuff onto which the younger rocks accrete themselves, stick. So in terms of North America, it is the superior craton. Now the superior craton is exposed in Greenland, in Canada, Ontario and Quebec especially, and in some of the more northern US states like Vermont, you might get a bit of it there. So, in terms of what you have, it's a mixture of Archean and Proterozoic rocks, but the craton itself is much larger. However, the vast majority of it is actually covered by younger sediment, so you can't see it. So that area is called the platform. So you have the bit that's exposed, that's called the shield, and you have the bit that's buried, that's called the platform. And the two of them together are called the craton. So what else do we find in the Proterozoic? Well, we begin to see the first pristine sedimentary rocks appearing. So we have the first rocks that have not been destroyed by metamorphism. We also begin to see the first definitive signs of life. So we see this in the form of stromatolites. You can see the stromatolites down here on the bottom left there. So stromatolites are essentially colonies of blue-green algae. So they're photosynthesizing organisms, and they form these columns of material. And one layer grows on top of another layer, grows on top of another layer, and eventually it builds up to form these large column-shaped masses. Now, the thing about the stromatolites is obviously these column-shaped masses get incorporated into the sediment, and obviously they become part of the sedimentary rock where they become fossilized. And so we see stromatolites beginning to appear in the Proterozoic. Now, this is very, very important because, as I just said, stromatolites are made from photosynthesizing algae. Okay, so this is telling us we now have algae which are producing taking carbon dioxide from the atmosphere, and they're producing oxygen. We also have evidence of mats of bacteria and algae which are also photosynthesizing, so they're taking carbon dioxide from the air, replacing it with oxygen. And this, we also have these two things, but that also means there's going to be lots of algae floating around in the top of the ocean, also madly photosynthesizing, taking carbon dioxide from the atmosphere and replacing it with oxygen. So what we begin to see in the Proterozoic is we begin to see the amount of carbon dioxide going down and the amount of oxygen going up. And we can see this in the types of rocks and minerals which are present. Now, the most important rock that begins to appear in the Proterozoic, which is the result of changes in the atmospheric composition, so it's because the atmosphere becomes more oxygen rich, are banded iron formations. So banded iron formation is exactly as it sounds. It's a rock which is banded, so it has lots and lots of layers, and some of those layers contain lots and lots of iron minerals. Now, these iron minerals are iron oxide minerals, so obviously in order to make them you need oxygen. So that's a good indicator that there was lots of oxygen around. Now, banded iron formations are important to us as geologists because it obviously tells us, it gives us a good idea when the amount of oxygen in the atmosphere and the oceans became quite high. But also, banded iron formations are the primary source for iron. They're the stuff that we mine now to get iron out of the ground. So what else do we see? Well, we also have the first appearance of organisms which we believe used oxygen to respire. Now, the oxygen concentration was getting to the point when now organisms could start to use that as part of their respiration process. So before that, organisms essentially used the process of fermentation to produce energy. But now, all of a sudden, you have organisms that photosynthesize, and you also have organisms which can begin to use that oxygen to actually respire. And so we have the first organisms that actually require oxygen to live. We also have, right at the end of the Proterozoic, we have the first appearance of complex fauna, and they're called the Ediacarian fauna. And they were initially discovered in Australia, but we have examples from them pretty much everywhere apart from Antarctica. And they occur right at the end of the Proterozoic, and part of the Ediacarian fauna contains several groups that we see now. So we have groups like the jellyfish appearing as part of the Ediacarian fauna. We have very, very early arthropods occurring as part of the fauna. We also have very, very early segmented worms appearing as part of the fauna. So, we start to see some of the groups which are present now beginning to appear in these very, very early soft-bodied organisms. But they're very important to us because they're the first indicators we have of multicellular complex life. Okay, so that's why they're so important to us, and we see them right at the end of the Proterozoic, just as we're about to go into the Cambrian. So what happens as we move into the Phanerozoic? Well, as we move into the Phanerozoic, obviously we move into the Paleozoic, and the start of the Paleozoic is shown by the Cambrian Explosion. And the Cambrian Explosion essentially is the appearance of numerous organisms which have shells. So you can see some of them down here. So we have organisms like trilobites appearing. We have organisms like brachiopods appearing. We have organisms like bivalves appearing. Okay, so we have lots of shelly life making their first appearance. We also have the first appearance of very primitive fish in the early Paleozoic, so the Cambrian. So this is what marks this transition from the Precambrian to the Cambrian. So in the Precambrian, any life was pretty much soft-bodied. There is some indication that some very, very late members of the Ediacaran fauna might have had, somewhat shelly bodies, but that's a completely different conversation. Once again, historical geology. As we cross the boundary from the Precambrian to the Paleozoic, we see this sudden appearance of hard-bodied organisms, and so that means they can be fossilized and incorporated into the fossil record, so we can see them, which is great for a geologist. So we see some really fun organisms appear in the Cambrian Explosion, because you have to remember, life is essentially experimenting. It's seeing what it can do, whether these body forms that it creates will fit the environments that the animal is living in. So we have organisms like hallucigenia making its appearance. So as you can see, a very interesting looking organism. We have organisms like, now I do hate pronouncing this one, Opabenia regalius. And you can see this one was a very interesting one. So it's got 5 compound eyes, has this very, very long proboscis with the mouth at the end, has a body that looks kind of like a trilobite, and the end of it, it ends in these kind of V-shaped tail, which looks almost like the tail of a fighter jet. So an extremely interesting looking creature there. And then we have some of the extremely weird creatures, like, I always hate pronouncing this one, like Veticolia, pronounced incorrectly, may I add. And you can see, in this instance, it's pretty much just a tail, a body, a mouth, and a set of gills. Yeah. So, a very interesting organism. In fact, it's so interesting that we actually find it a little bit difficult to know which group of animals it belongs to. So, yeah. So the Cambrian Explosion produced lots and lots of very interesting animals, because life, essentially, evolution, is testing out what body form suits what environment best. Now, the Cambrian Explosion is driven by the fact that, number one, the oceans become warmer. The oceans at the end of the Cambrian were quite cold because there was a big, massive glaciation going on, a big ice age at the end of the Proterozoic. As that disappears and retreats, all of a sudden the global oceans become a lot warmer. We also have the oceans become saturated with calcium carbonate, and so this is very, very good because it means organisms can now pull calcium carbonate from the water to make their shells. We also have the first appearance of, not the first appearance, but we have the appearance of large quantities of passive marine environments. So a passive marine environment is something like the east coast of the US. So think about the east coast of the US. What's going on there geologically speaking? Rivers are depositing sediment. That's about it. So in terms of what's going on, those are referred to as passive margins. They are, from a geologic point of view, pretty dull. And so life loves pretty dull. It's safe, it's boring, life can do its thing there. And so the appearance of lots of these passive margins suddenly means that life has a nice, safe environment in which evolution can, take place, and evolution will start to find the best body form for that environment. And the final thing that drives the Cambrian explosion is the appearance of predators. So, as far as we know, the Ediacaran fauna, they were probably mostly filter feeders. So we don't know whether any of them were predators. What we do see, though, in the Cambrian is we begin to see the first appearance of predators. So, for instance, if we look down here at Hallucigenia, well, you can see it's got a row of spikes on its back. The only reason to have those is for protection. So that means clearly there were predators around. And so what was the biggest and baddest predator? Well, here it is, Anomalocaris. They probably would have reached a maximum of about 2 meters in length. And you can see they have these eyes that stick out on stems, stalks either side the body. They have these 2 appendages at the front, which have these huge spines in them. Now they're for grabbing the animal that it wants to eat. The body itself essentially is this, as you can see, is an elongated body with these, how can I describe it? With these wings either side, and it would have moved through the water in a kind of sinusoidal motion. And then, of course, this is where the real problem, this is where the real danger was. That's the mouth right there. So if you look at this fossil here, you can see there are the eyes. Here are the 2 appendages. You can see in all these pictures here, these huge spines coming off them. So if these things got you, you're in real trouble. Your chance of escape was pretty low. And then over here, we actually have an Anomalocaris mouth. And you can see it has all of these teeth, essentially, and the mouth would have just bitten and ground down into the fossil, essentially, until it eventually, reached the good bit of the animal that it wanted to eat. So Anomalocaris was an extremely interesting and extremely frightening predator, and this was one of the predators that was driving evolution. Because if you're at constant danger of being eaten by something like this, you have to essentially come up with strategies that allow you to not be eaten by Anomalocaris. So that's going to help to drive evolution forward. Okay, so what about the rest? So that was the Paleozoic. So the Paleozoic is quite interesting. It sees the appearance of the first shelly life. We have plants appearing on land. We have the amphibians essentially migrating from the oceans and the lakes onto the land. We have the appearance on land of the seedless vascular plants. Okay, and the gymnosperms, essentially they start to form huge forests that cover the continents during the Paleozoic. We have obviously the transition from amphibians to reptiles, and then we have the transition from reptiles to very, very, very early reptilian mammals. So then at the end of the Paleozoic, we obviously have this huge mass extinction event, the Paleotriassic extinction, and then we move into the Triassic. As we move into the Triassic, obviously we then see the first appearance of the mammals, the first appearance of the very early dinosaurs. The dinosaurs begin to establish themselves. Dinosaurs become essentially the major group during the Jurassic and the Cretaceous. Mammals during this time period are on the whole quite small. Think kind of, shrew, mice, rats, that kind of size. There are a few larger examples, but on the whole, mammals are pretty small. Because, let's face it, they're hiding from the dinosaurs. They've got to be able to hide in small spaces. We see the first appearance of very, very early birds. And we see the appearance of the angiosperms, the flowering plants, who eventually will establish themselves as the dominant plant group. So, in summary, if we just have a look here, in the Precambrian, we have very simple life, soft-bodied, and so obviously it doesn't fossilize very well. So typically throughout most of the Precambrian, we have no fossils. So the only thing we can look for are the structures left by the fossils. So things like stromatolites. As we move into the Paleozoic, we see the first appearance of shelly life. So we see organisms like corals, clams. We also see a group of organisms called the crinoids. Okay, so crinoids, think of something that looks kind of like a sunflower attached to the seafloor. It's a filter feeder. If you don't know what it looks like, go to Google it. It's quite cool. It's part of the same group as starfish and sea urchins. We also have the appearance of fish. We have plants forming on land. We have insects on land, and we have the amphibians making it onto land. And then we have the amphibians transitioning to the reptiles, and the reptiles transitioning to the very, very early reptilian mammals. So as we move from into the Mesozoic, we obviously see the appearance of the dinosaurs. We see later the appearance of the birds, and we see the appearance of the flowering plants. And then obviously as you move into the Cenozoic, well, that's where the mammals really make their move. Initially it's the birds, but eventually the mammals begin to outcompete them, and the mammals become the dominant group. We also see the angiosperms really essentially establishing themselves in the Cenozoic. So we begin to see the angiosperms essentially pushing back the gymnosperms and the seedless vascular plants. So they're essentially pushing them back into more limited environments. And the angiosperms essentially now make up about 90% of all plant life. We also especially begin to see the appearance of grasses, which are part of the angiosperm family. And so grass is very important because grass all of a sudden becomes a major food source for a whole range of mammals. Okay, so what about the Paleozoic in terms of the continents? So throughout the Paleozoic, most of the continents were separated, they were either independent of one another or they were part of two large land masses. The first large landmass was called Gondwana, or Gondwanaland, and it was found in the southern hemisphere, so south of the equator. And it consisted of South America, Africa, India, Australia, Madagascar, and Antarctica, all combined together into one big landmass. And that was normally south of the equator. North of the equator, we had the landmass of Laurasia, and that consisted of Laurentia, which was North America, or will become North America, Baltica, which is mostly Europe, and Siberia, which is obviously a large part of Russia and Central Asia. And so those continents were combined together to form one landmass, which is referred to as Laurasia. And I can't remember the approximate date, but about cripes, I can't remember this exact number now. This is rather embarrassing, so I'm just going to not remember when it is. But essentially, they eventually crashed into each other, and the resulting set of mountains was absolutely huge. It was the size of the Himalayas, and the modern day exposure of those mountains in North America, at least, is the Appalachians. So the Appalachians are produced as part of this collision between Gondwana and Laurasia. So this collision happened in the Carboniferous, and so it continues into the Permian. And by 252 million years ago, what we begin to see is the supercontinent that we have, Pangaea, is beginning to tear itself to pieces. So about 252 million years ago, we have this mass extinction, but we also see Pangaea begins to pull itself apart. Now, Pangaea itself was quite interesting. It had lots and lots of forested land along the coasts, but within the center of this very large continent, it tended to be quite dry, which means you had very large areas of desert in which we formed rocks like evaporites. Now, obviously, these dry conditions were not suited for animals like amphibians, who obviously like wet conditions. However, this transition from amphibians to reptiles essentially created a class of animal which was very happy in these dry conditions. So this drier land, which was not accessible to the amphibians, was all of a sudden wonderfully accessible to the reptiles. So it became a good refuge for the reptiles to live in. It was their preferred terrain, and there wasn't another animal which was competing against them. So that was pretty good as far as they were concerned. So at the end of the Paleozoic, of course, we have Pangaea begin to tear itself apart. But we also have this Permo-Trias mass extinction, which is also referred to as the Great Dying. How bad was it? Well, it was pretty bad. 90% of marine species and 70% of species on land. So, as I said, it was about as close as we've ever come on Earth to completely resetting life on Earth. So, yeah. So that marks the transition between the Paleozoic and the Mesozoic, this huge mass extinction in which numerous species are lost from disappear from the fossil record. So in terms of the Paleozoic itself, so in the early Paleozoic, most of the action is focused in the oceans. So we have the corals, the crinoids, the mollusks, the trilobites, we have marine snails, so gastropods, we have shelled cephalopods, and we have primitive fish making their appearance. As we move into the middle Paleozoic, we see fish begin to diversify a little bit. We see the ammonites making their appearance. So these are cephalopods which have a coiled shell. Okay, so think of an octopus living inside a coiled shell. We have insects making their way, well, appearing on the land. We also have the first plants appearing, and we have the first ferns appearing. And so we have the first appearance of these seedless vascular plants and gymnosperms appearing on land. Now, these seedless vascular plants and gymnosperms will eventually start to form huge forests on the land. So by the time we make it into the Paleozoic, we have these huge, massive, extensive forests everywhere along the, well, I shouldn't say everywhere, mostly along the coast of the supercontinent of Pangaea. As I said, the centre is quite dry. So in the late Paleozoic, it's mostly the interesting stuff is mostly focused on the land. So we see the amphibians move from the oceans and seas and lakes from essentially wet conditions onto the land. And the amphibians eventually transition into the reptiles. Okay, you can see in this picture we have a couple of reptiles here called fin-backed reptiles. And you can see the fin right there. Once again, if you want to know what that was for, historical geology. And we begin to see the reptiles begin to evolve, and they will eventually make it into a group called the therapsids. And the therapsids are essentially slightly mammalian reptiles. So they're the start, essentially, of the evolution of mammals. So as we move into the Mesozoic, what's happening with the continents? Well, do you know what? We'll discuss that in part 3. So once again, stop here, get up, have a walk around, get some water, some tea, some coffee, have a snack, and then come back when you're ready for part 3.